Alright, hi YouTube, this is Mr. Lim here again, and this is our, sixth video on volumetric analysis about now we start our calculations. Okay, so we're going to start with fairly simple titration calculations where you have a bit of dilution and aliquots being used, and then we'll work out how to pick the right equation to use when we're using aliquots and dilutions. Right, so when titrations are completed, they often involve dilutions and aliquot processes. Okay, so what are these things? So a dilution is when distilled water is added to the solution. In a dilution, the number of moles is kept constant and only the volume and concentration change. So when you dilute something, you don't change the number of moles because you're just adding water, right? However, aliquots are different. It's when a portion of a solution, so say you have a 500 ml solution, you take 20 ml out, is taken from the sample, and you take that 20 ml and then you titrate it. Generally, all solutions that are put into the conical flask are aliquots of a particular sample. In an aliquot, the concentration of each part is equal. However, the volume and the number of moles change. Okay, so in dilutions, your number of moles is kept constant, right? And volume and concentration change. Whereas in aliquots, your concentration stays the same. However, your volume and your number of moles change, right? So when doing calculations, it's important to you to visualize the process that is occurring so you can follow the calculation appropriately. So we're going to just go look at a couple of calculations and do them and draw them out. Okay, so let's have a look. First one, okay, a solution of ethanoic acid, and I always would recommend that you highlight the information and you color code it by what chemical there is. So I've got a solution of ethanoic acid is titrated against standardized sodium hydroxide, and the word standardized there means that you know its concentration, right? To determine its concentration being the ethanoic acid. 25 mils of 0.58 moles per liter sodium hydroxide, so these two values are in blue, was transferred into a 200 ml volumetric flask and made up to the mark, so that's also in blue. 20 ml aliquots of this sodium hydroxide, so 20 ml aliquots, also in blue, is then titrated against the ethanoic acid and the results are gathered. Okay, so these results are all related to the volume of ethanoic acid added to the sodium hydroxide aliquots. Okay, so let's draw this out first and then let's start this calculation. So let's have a look. First of all, we start off with some standardized sodium hydroxide. Okay, so sodium hydroxide, and we know that there are 25 mils of 0.58 mole per liter. Okay, so this is our standardized substance, which means that we've probably just standardized it and we're using it to do other stuff with it. All right, so we take that and we put it into a volumetric flask. Okay, it's still NaOH, but now, however, it has a 250 ml volume. Okay, we took that 250 mils and then we take 20 ml aliquots of it. Okay, so we're taking aliquots out using a pipette. Okay, 20 ml aliquots of NaOH still, right? And we're putting it into the conical flask. Okay, over the conical flask is the burette. Okay, so inside the conical flask is the NaOH, the 20 mils of a certain concentration, which we haven't worked out yet. And in the burette, we've got the ethanoic acid, okay, which we know the titer volumes for from this table, okay? So that's a visualization of it. And then we have to think, where is our known substance? Our known substance is all the way over here. Oops, I don't want to do that. Undo that. All right, so our known substance is all the way over here. This is where we're going to start the calculation. We're going to start the calculation here, and we're going to follow it along until we get the concentration of this CH3COO titer, because that's what we're asked to do. All right, so this is how you would do it. All right, so let's move this down a bit, maybe shrink this a bit. First of all, I would always recommend writing out the chemical equation that is occurring in this particular reaction so that you can just show it that you know what the equation is and how to balance it. Okay, so sodium hydroxide and calcium, sorry, not calcium, ethanoic acid will make sodium ethanoate and water, which is balanced in itself. All right, so now that I have that, I have to start with where I know, which is the sodium hydroxide. So I'm working out the number of moles of sodium hydroxide, which will be equal to CV, which will be equal to 0.58, which is its concentration times its volume in liters, 0.025. So 0.58 times 0.025 is 0.0145 mole there. And I'm going to save that as A. Right. Now that I have that, I'm going to now be able to work out, so I'm moving this way, so I've just solved for this, I'm moving this way, now I got to solve for the concentration in the thing. All right, so now remember this is a dilution, so of a dilution, it's the number of moles stays the same. Now what I do recommend is with these calculations, you start to annotate what you're solving. So I already ask you to write down N of whatever you're solving here. Now we're going to go for next level, where we're going to write down what because there's going to be so many sodium hydroxides here, right? We have to say which sodium hydroxide this is. And this is in the 25 mil, and that's a unique aspect of this one here, all right? Of a variety of other names that you can use, like the original sample, so on and so forth, all right, or the standardized sample. So that's the number of moles in there. Now we can work out the number of moles of NaOH in the 250 mils, or you could have said in the volumetric flask. Okay, so if we need to know that, we have to remember that when we dilute something, we keep the number of moles the same. So the number of moles of 250 is equal to the number of moles in 25. However, we are going to have a different volume and different concentration, right? Actually, we don't even need to do that, really. That's if you want to work out the concentration of that substance in there. We haven't been asked to work out the concentration, but we will do it anyway, and then we'll have a look, all right, at another way to do it. Okay, so you can work out the concentration of this NaOH 250 by saying, okay, well then it's equal to N over V, where N is A, because it's the same, okay? So this value here, remember, is A, right? And therefore that makes it that value there, which means that we can use it for this concentration here. So that value A over volume of 250 mils, which is in liters, is that. So therefore it is A divided by 0.25, which is why we save numbers, 0.058 mole per liter. Okay, now, we technically don't need to know the concentration of this, right? Because whatever concentration is in this volumetric flask, right, we know the number of moles. And the number of moles is always going to be important. So if we know the number of moles already, we don't need to do anything else, because what we're going to do is we're going to think, okay, if I know the number of moles in there and they're all evenly spread out, if I take a small portion of it, like the 20 mils, therefore I'm going to take a fairly consistent portion of that. And so therefore, if I can just work out how much it took out, that will help me with the rest of this calculation. All right, so I want to find out how much is in 20 mils from that 250 mils. So what I would say then is that, okay then, if I can work out the number of moles of the NaOH in the 20 mils, because what it will be is that it will be a fraction of what it is inside the volumetric flask. Okay, so if the number of moles in the 20 mils would be something along the lines of the number of moles in the 250 mils times, now remember it's going to be a fraction of it, and the fraction is actually 20 over 250, which is, if you wanted to know, the volume of your unknown over the volume of your known. And if that looks familiar, then it's from the stoichiometric ideas. This is all about ratios. Okay, so you'll notice that I also didn't have to put them in liters. You have to keep them in the same unit, but it doesn't matter if it's in liters or in milliliters. Okay, so that's the number of moles. It will be 20 over 50, 20 over 250 times A. So A times 20 divided by 250 will be equal to 1.16 times 10 to the negative 3 moles. That's how many moles are in a 20 ml aliquot of that sodium hydroxide. Okay, so now we are still moving across. We've just solved for that one there. Now we're moving into here, over into this reaction between the burette and the pipette, not the pipette, the conical flask. Okay, so I have a number of moles of NaOH 20 mils. And I should know from the equation, because now I'm kind of here in my diagram. The only way that I can go is up to here because that's what I'm trying to solve. All right. So the number of moles of ethanoic acid will be equal to the number of moles of sodium hydroxide times 1 on 1. Where did I get this from? It'll be from this, the balanced equation. All right. Which means that they are equal, and that I have 1.16 moles times 10 to the negative 3 in each of the titers, or at least the average titer. Okay? So, what we can then do is we can work out, we are now in the burette, okay? We have the amount of ethanoic acid that was delivered to react fully with a 20 ml aliquot of sodium hydroxide. Okay, we have the volume. We have the number of moles, but we don't have the volume to work out the concentration. All right. So, what we need to do then is we need to have a look at what we've got over here. These titer values. Those titer values can be used to work out the difference of stuff. Okay, of the difference in the amount that's added of ethanoic acid. So I'm going to save that value that I've already got as B. All right, then I'm going to work out the differences between this. This is why you need to learn how to save values. Okay, so this first value is 20.54. You can actually do this at the beginning as well, because if you're not sure about how to continue on, at least you've solved for one part of it, and that will get you a few marks. Okay, so this is 20.02. This is 20.04, so those two are good, they're within 0.1 of the range. And then the last one, 19.98, which means that they are all within 0.1 of a mil, those last three, which means that I can take the average of those three. Okay, so if I take the average of those three, I don't have to show them in my working, but I can. All right. So the number of moles not the number of moles, the volume of the titer of the ethanoic acid titer, and this is also the titer, okay, will be equal to 20.02 plus 20.04 plus 19.98 all over 3. And what do you get? Some value. 20.02 plus 20.04 plus 19.98 divided by 3 will get me 20.01 mils. Okay, so now that I've got that, I have the number of moles and I have the volume. I can work out its concentration. So the concentration of the CH3COOH, the titer, will be equal to N on V, which will be equal to 1.16 times 10 to the negative 3 mole, which I would have saved as B, and 0.001, right, which is the volume there, okay, and you get as the answer 0.058 moles, okay, and that's the concentration, so it's moles per liter, whoops. And that's how you do the first one, okay? So you'll notice that you've got both a dilution and aliquot in here, all right? So you've got to just work out when to use the various ratios and the various equations. The dilution one is C1V1 equals C2V2, which is when you have equal number of moles effectively from your undiluted and your concentrated solution. And then your aliquot is a portion. So remember the concentration stays the same, but the number of moles and volume changes. So N1V1 equals N2V2. All right, and you should be able to see where these ones have been used. This dilution calculation was used here. Well, actually, technically, it kind of was used here. Okay, right. But that one there could have been done. Actually, no, yeah, that's fine. Yeah, right. The combination of this and this make up that equation, right? And then the aliquot calculation was done here, okay? Work out the 20 mils from the 250 using that, okay? So that's that one there. Okay, so this one here, I've already pre-done it, and we're just going to walk through it, and so I don't have to write it out and do the calculation. So a solution of calcium hydroxide is titrated to determine its percentage by mass. 5 grams of the calcium hydroxide solution was placed in a 100 ml volumetric flask and made up to the mark. 20 ml aliquots of this solution were then titrated against a standardized solution of hydrochloric acid with a concentration of 0.0246 moles per liter. It was found that an average of 23.46 ml of the hydrochloric acid solution was required to reach the equivalence point in the titration, determine the percentage by mass of calcium hydroxide solution. All right, so again, highlight the information so that you can see which numbers are related to which chemicals, right? And then you can see that there's only 2 chemicals in here. Then again, draw it out so you can see. Here I have 5 grams of calcium hydroxide, okay? Of 5 grams of calcium hydroxide solution with an unknown concentration in terms of percentage by mass. Okay, what did I do with that? I took that 5 grams and I put it into a 100 ml volumetric flask, right? So now I have 100 mils of that solution. I then took 20 ml aliquots of it in a pipette, and if I take 20 ml aliquots of it, it has to go into the conical flask somewhere, right? Then I have the hydrochloric acid as my second chemical, and I know its concentration and its volume. So where do I start? I start out here with the HCl, and then I'm going to move my way back through this diagram to work out the concentration on the left-hand side. Okay, so that's why we draw a diagram, so we can visualize it and we can see where we have to go through and what calculations we have to do. Okay, so first of all, you write out your equation for the reaction at the titration, at the titration. So HCl, calcium hydroxide, calcium chloride to make water. There's that equation. Then I start with what I know. Okay, so I start with what I know. I'm doing the HCl. Okay, so the HCl, again, make sure that you annotate what you're solving. The HCl titer is 0.0246 times 2.2346, which is the 2 values that were given in the question, and I have 5.77 times 10 to the negative 4 moles, which I saved as A. Right? Now, I'm up to this part of the, I'm up to here. I just solved the amount that's in the burette, or in the titer that went into the conical flask. So now I can work out the number of moles of calcium hydroxide in the aliquot, because it'll be related to the number of moles of HCl in the titer, right? And therefore I'll be here in my diagram. I work out that as B, okay, 2.86 times 10 to the negative 4. Now that I'm here, I have to go backwards and I have to work out the number of moles in the aliquot. Actually, I did that already because that's what the aliquot was. That was in the conical flask, so I'm now here. Now I need to go back to the volumetric flask of calcium hydroxide. Now, when I take out an aliquot of that, what I'm doing effectively is I'm taking out a portion of it. So if I have the number of moles in the portion, I can work out the number of moles in the total using my aliquot equation. Okay, so the number of moles of calcium hydroxide in the volumetric flask will be equal to the number of moles of calcium hydroxide in the aliquot times it's fractional volumes going back upwards because I started with the portion and I need the total. So I got the total over my portion. Okay, and I get a value here of 1.44 times 10 to the negative 3. Once I have that, I should be able to understand that the number of moles of calcium hydroxide, I'm going backwards this way, in the initial solution. So the number of moles in the volumetric flask is equal to the number of moles in the 5 grams, which is that value there, which that means I can work out then the mass of that calcium hydroxide here, okay? And I've worked out that mass of calcium hydroxide to be 1.1069, and therefore I can work out the percentage of the calcium hydroxide because I've got the mass over its total mass times 100 gets me 2.14%, okay? And that's what it was asking for there, the percentage mass. And so what I did was I went backwards through this diagram, backwards through it to get all the way back to here to get the percentage of that one. That's it for that one. Alright, so this one is another one from an exam, so let's go read through it. In 1971, on the 7th manned Apollo mission, Apollo 13 launched, expected to land the moon. However, one of the oxygen tanks exploded. Mission is aborted, but needed to get back to Earth. There needed to be problems to be solved, blah, blah, blah. Okay, so here's a little bit of information about it. Okay, blah, 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 blah. But we really start about here. One of the problems encountered was how to remove the carbon dioxide breathed out by the astronauts from the atmosphere in the spacecraft. This was done by reacting it with lithium hydroxide, which was housed in canisters. Okay, so we're getting rid of carbon dioxide by reacting with lithium hydroxide. Okay, so what's the equation? So here it is. Just really a reminder that you really need to know your ionic formulas so you can answer these questions and not have to worry about just not being able to balance it. Anyway, so here starts the titration. On returning to Earth, a partially used canister was analysed to determine the percentage of lithium hydroxide remaining. So you've got to remember, right, it's turning from lithium hydroxide to lithium carbonate, which means that inside this canister, at the end of it, is going to be some lithium hydroxide, but the majority of it, I guess, is going to be lithium carbonate. Okay, so there's going to be a mix of this stuff here and this stuff here. Two different things inside these canisters, right? Because I think that's what tricked a lot of kids with this particular question because they got really confused later on. A 12.33 gram sample of the canister contents was dissolved in distilled water and sufficient barium nitrate was added to precipitate the carbonate ions. Notice, however, that this barium nitrate, there's no information given about its mass or its concentration or anything, right? The idea is that this barium nitrate is getting rid of the carbonate ions so that it's only remaining the lithium hydroxide. So it gets rid of the lithium carbonate and it only allows to remain the lithium hydroxide. Okay, so that's what we're trying to solve for anyway. Okay, so that's what they did, they precipitated it out. Solution was filtered and transferred to a 500 ml volumetric flask, which is then filtered and marked. 20 ml aliquots of the solution were transferred into a conical flask, titrated against standard hydrochloric acid solution. Okay, these results were obtained from the titrations. Again, please try and highlight things by their chemicals, and so we should be able to work out what this table should be, what color should this table be highlighted. So remember, this is the titer, okay? So if this is the titer, that means it has to be whatever's in the burette, which we can work out as hydrochloric acid because 20 ml aliquots of that solution, which was the lithium hydroxide, is in the conical flask because it's the 20 ml aliquots of it. Okay, so this titer is hydrochloric acid. Okay, so here's what we could again draw out what we know. Okay, so what do we know? We know that there's a lithium hydroxide, lithium carbonate mix until we add barium nitrate, in which case now we have only a lithium hydroxide solution with the VA03 filtered out at some point. All right, and then we transfer it to 500 ml volumetric flask, of which we take 20 ml aliquots, dump it into the conical flask, and react it with HCl. Okay, so first of all, first reaction, lithium hydroxide and HCl, making lithium chloride and H2O, so nice and easy. And where do we start? We start off with what information we have. We have the titer volumes. We have the titer volumes, which can go into that one is there as well. Okay, so we have a tighter volume of 16.33, which is just solved by picking out the three concordant results, which are these three over here. Okay, and then we work out the number of moles of HCl from that. Okay, so here's the number of moles of HCl using the volume and the concentration. Here's the number of moles in the titer. So in terms of the reaction, we are, where are we? We are, let's make this one a bit smaller. Right, we are here. We've worked out the number of moles in the burette. Okay, we know that gets titrated with the conical flask, so therefore we can work out the number of moles of lithium hydroxide in any one aliquot. Okay, that's the number of moles of lithium hydroxide in all the aliquots on average. Okay, so now we're up to here. Then we need to work out the lithium hydroxide in the volumetric flask. Now remember, the pipette is a portion, or the aliquot is a portion of the volumetric flask, or a fraction of it, so we can use that fraction idea to work out the total. Okay, and remember, this is again the aliquot calculation where the concentrations are the same, but the number of moles and the volumes are different. So we can then now use the lithium hydroxide equation to, first of all, we know that the lithium hydroxide must be this many moles, and therefore that's in the aliquot. And so therefore, if we use this fraction, we can get the amount in the volumetric flask as this value here. Okay, so now we are up to the volumetric flask. We need to keep on moving backwards. We need to work out how much lithium hydroxide was in that solution. Okay, the number of moles in the 12.33 gram sample was this, because it's the same, because all of the sample was transferred to the volumetric flask. So it's that number of moles in the 12.33 gram sample. I get my lithium, molar mass of lithium hydroxide, multiply it by the number of moles, and I get the mass of it. And then I can get the percentage of it if I know the final mass and the initial mass, okay, which was then 9.2%. Okay, so this is a bit of an example of how you really need to draw this thing out to let you walk it back through, and you need to pay attention to, they'll throw in a couple of extra chemicals in there for no reason, just to see if you know and you understand what's actually going on. Okay. Okay, so next question is about acid rain. Okay, so acid rain is bad from the gases from burning of fossil fuels, and it makes the rain acidic. Okay, so now that's the first paragraph. So let's have a look at the second paragraph over here. Testing was carried out on a rainwater sample. That's our first chemical, taken near a coal-fired power station by titration using sodium hydroxide solution. Okay, so that's sodium. That's our second chemical. Standardization of that sodium hydroxide solution was carried out before it was being used in the titration. An anhydrous sodium carbonate solution, primary standard, was used to standardize a hydrochloric acid solution, which was then used to standardize the NaOH. So what have they done here? Where have they started off? They've started off with the primary standard, the anhydrous sodium carbonate, with which they've used to standardize or find the concentration of HCl, of which they've used to find the concentration of NaOH, of which they've used to find out the concentration of acid within the rainwater. Okay, why didn't they just do the rainwater against the anhydrous sodium carbonate? I don't know, but generally it's just not done that way. Okay, so that's the overall entirety thing. There's like two parts of it: the primary standard versus the first standard, the first standard versus the second secondary standard, and then the secondary standard to the sample, which is like three different things. Okay, so let's go walk through it. They start off with the first part. Sodium carbonate, okay, which is our primary standard, heated to get rid of the water for 1 hour, and then it was this many grams, which is a really small amount. You wouldn't even be able to get that on a scale, really. All right, dissolved in distilled water to make 2 liters of primary standard. Then 3 25 ml aliquots of HCl were titrated, and an average titer of 16.4 was required for neutralization. Okay, so again, the average titer of 16.4, you should know that it's sodium carbonate because you've got aliquots of hydrochloric acid, so the other chemical must be the titer. All right. So demonstrate by means of calculation that the concentration of HCl is that. Okay, as I always say, you should draw it out first. Okay, so here's my sample. 6.08 times 10 to the negative 4, which is a very small amount. Gets dumped into a volumetric flask, a 2 litre one, and filled up to the mark. Then, interestingly enough, this gets put inside the burette. So normally we put the aliquots inside the, we actually always put the aliquots inside the conical flask, but normally we take the thing that's the volumetric flask and put it into the burette, the conical flask, but this time they're putting it into the burette. But, that doesn't actually make a difference to the calculation. It does, however, make a difference to your diagram, so you should always follow it through. So where do we start? Interesting thing about this question is that because it gives you this particular piece of information about the suggested thing, technically you could start here, okay? But I haven't started from there. I've started from the other side. I've started from over here, okay? And then I'm working my way towards the right. So let's have a look at what I did, okay? So first of all, I work out the number of moles of sodium carbonate inside that beaker, okay, just by using M over big M. And now I'm in this part here, I got the number of moles of that. Now that I got the number of moles of that, I need to work out the number of moles in that volumetric flask, which if you remember, it's going to be equal, okay? The number of moles in the beaker is equal to the number of moles of the substance in the volumetric flask because they completely dissolved it, all right? Then, the number of moles of sodium carbonate titer and the number of moles are in the volumetric flask, because remember, they are two different things, okay? So, where are we going? So, number of moles in the titer, which is here, okay? The number of moles in there is equal to the number of moles in here, but it's a fraction of it, okay? Because we're taking a portion out, putting it inside here. And so that titer there is a portion of this 2 liters, okay? So that's how you show it. You get the number 16 is on top and 2000 on the bottom, and that's going to be the fraction of the titer going to the volumetric flask, all right? That's 4.7 times 10 to the 8 moles, blah, blah, blah. Now that I have the number of moles of Na2CO3, I should work out the chemical equation for it, okay? Once I've got the chemical equation for that, I can start working for the number of moles of HCl, because that's still our unknown. Okay, that's still our unknown. So we can start working on the HCl. The HCl has the aliquot of HCl going to be 2/1 moles of the Na2CO3. Okay, so I've got a 1:2 ratio here. Okay, 1:2 ratio there. And then I can work out the, because I'm going this way, started at here, been going this way. So I've got a 1:2 ratio here, and then I can work out the concentration in this via the volume that's there by the end of it. Okay, so that's that one there. That's how you solve that one. That's just the first part. Whoa. Okay, so the means of calculation that the solution is 3.76 times 10 to the negative 6, which it was. Okay, so let's start the next one. An average titer of 21.3 mils of standardized HCl. Again, we're using the color coding that we stick with before, HCl green and NaOH red. Required to neutralize 25 mils of aliquots of NaOH solution. Okay, so 21.3 mils was required to neutralize 25 mils of sodium hydroxide. Okay, so remember the sodium hydroxide is another secondary standard which we're using to eventually get to the rainwater. So again, we drew it out. Here is the HCl. It's delivered 21.3 mils with a certain concentration. So we know that value. And then we can work out the number of moles inside the NaOH. So that's what we did first, the number of moles of HCl in the titer. Then we worked out the number of moles of NaOH because that was from the titer. Okay, so you have to work out the number of moles of NaOH as a concentration, which gives you that value there. Okay, so now we have the concentration of the NaOH. We can go move on because the titer obtained for rainwater sample are shown below. Okay, the titer values. So titer for the rainwater sample, okay, are shown there. Average titer is we just use the 3 concordant results, which is within 0.1 of each other, and you get that value, so on and so forth. And then we get to the fun part. So the standardized sodium hydroxide solution can then be used for the titration of rainwater sample. Okay, 100 ml sample of rainwater was collected near a coal-fired power plant and is diluted with 250 ml of distilled water in a volumetric flask. Then 25 ml aliquots of it were used in the titration. So where do we start? We start off with the number of moles of NaOH over here, and then we work our way back this way. Okay? So if I'm starting at the NaOH, I got to work out the number of moles of NaOH, but you should also recognize that because you haven't been named an acid, but we're talking about acid rain, we can just have the following equation to work out the amount of water and stuff. So number of moles of NaOH is where we started with in the burette, and that gets you there. Then you need to work out the number of moles of acid, which is the rainwater acid, is equal to the NaOH titer times 1. Then I can get the number of moles in the number of moles of acid in the volumetric flask from the pipette. Okay, so from the pipette to a volumetric flask, again, the pipette is a portion of the total, so therefore I just find the total from the portion, and I get this value here. It's nice and easy. Then I can work out the amount of acid in the 100 mils from the volumetric flask, okay, which means that I need to use and find its new concentration because I used this one here for the acid. And then now we can work out the concentration because we have the number of moles and the volume. Okay, the volume, where did that come from? 0.1 mole, 100 mil here, the rainwater. Okay, so then I have that concentration there. Then I just do pH negative log that because you don't need to do anything else with the base hydrolysis or anything. So therefore, pH is 5.2. Right. So here are some tips for how to do calculations. Number one, you draw out the process. Drawing out the process really helps you allow to follow the diagram to get from your unknown to known, right? So therefore we can use it just to kind of guide us in how to remember stuff. Okay, so you highlight the info and you kind of color code the information by what chemical you're doing. Then when you're doing the calc, you got to show what you're solving by annotating the side bits. Okay, you got to read the question carefully because maybe they're asking for concentration and you've given moles, or maybe you're asking for pH and all you did was give concentration. You've got to read the question carefully after you finish it just to check that you're answering the right thing. If you do ever make a mistake and it's a big one and you need to start again, you don't just erase your answer. You write out your new answer first, then you erase your old answer. Why? Because if you run out of time, at least you can just quickly cross out your half calculation and just say, oh, yep, that old one, I did most of the steps right. That's fine. And then you'll get more. But also, if you don't know a step, okay, if you get stuck in a particular titration and you're stuck, you don't know where to go, what you can do is you can actually just make an assumption, especially if you know the steps beyond it. Because once you've made an assumption and you say, okay, well, it's this concentration, if that's what you're trying to solve, then you can, once you've made that assumption, then you can use that assumption for further steps and get follow-through marks. Okay, so those are just a couple of tips for calculations. It's a long video. I'm out.